Hello everyone, welcome. This is the last class of this week. What we have discussed so far in this week is we discussed what is virtual work method. Then we saw that the principle of virtual work can be how the principle of virtual work can be translated to a method which can be used to determine unknown displacements at any given point for statically determinate structures. Okay. Now, this method is unit load method. We demonstrated the unit load method in truss problems, and then what we are going to do today is we will see what is the form of unit load method for beams and frames. This is the first thing, and another important thing that we are going to do is this virtual work principle. We'll see that it gives from virtual work principle. We'll see some of the interesting behavior of structure, and this principle gives us some insight about the structural behavior when a structure is subjected to certain load. Then it undergoes deformation. It will develop some internal forces, but how these internal forces are distributed and how these internal forces are related to this displacement, and when in that relation do they follow certain interesting trend, that we'll try to understand through virtual work principle. Okay, another important thing is the principle. As of now, what we have discussed, we have not made any assumption about the material. Material has to be linear elastic. The principle is applicable to any material, even if you have inelastic behavior in the material. But since in this course we are not talking about inelasticity, we are only concentrating on the linear elastic structures. Therefore, the applications of the virtual work is limited to only those problems. But in principle, this can be equally applicable to other material as well. So, today what we are going to do is the principle of virtual force, which will eventually give us unit load method. We will see what is the unit load method for beams and frames. As far as the application of unit load method for beams and frames are concerned, we won't discuss that in this week. When we talk about different methods to find out deflection of beams and frames, there we will demonstrate the unit load method. Okay, so let us quickly have some review of the method that we discussed so far. This is the gist of the method. Okay, what it says that if you have two systems, one is system 1, which essentially gives us the force field, and system 2, which is displacement field. Now, the force and displacement field, they are conjugate to each other, but they do not have any cause effect relationship. It's not that the displacement field is caused due to the force field. Okay. Now, force field should be such that they satisfy the equilibrium. They should be statically admissible, and the displacement field, which is system 2, they should satisfy the internal compatibility. Now, if we have two such systems, then principle of virtual work says that the external work done equal to the internal work done, means the work done by the external forces on the conjugate in the external displacement, which are the conjugate to external forces, is equal to the internal forces, work done due to the internal forces associated with the conjugate displacement, internal displacement. Okay. Now, then this is the general expression for principle of virtual work. Then we have two special cases depending on which system is real and which system is virtual. Now, if we take system 1 is real, the force field is real and the displacement field is virtual, then the method says that it is a principle of virtual displacement. And if we have the opposite, means it is, if the system 1 is virtual, the force field is virtual, and system 2 is real, the displacement field is real, then it is principle of virtual force. It is the principle of virtual force which we have translated into a method which is unit load method. Okay. Now, let us see this also we discussed in some of the in one of the class in that if we take a beam which is subjected to a concentrated load, say F at any given point, and the corresponding displacement in the direction of the force is d, then the external work done by this force is equal to F into d. And similarly, if we have a moment at B and the associated displacements in the rotation, and then the moment external work done by this moment is equal to mb into theta b. Now, if this displacement field is virtual, then this work will be the virtual work. Similarly, if the displacement field is real, but the force field is virtual, then this work will be virtual work. Okay, but the computation of the virtual work, that the force and multiplied by the associated displacement and the moments multiplied by the associated rotation remains same. Okay, now, so this is external work. Let us understand what is internal work. If you remember in truss, if we apply some load on truss, then every member will be having some internal forces, okay, and because of these internal forces, the member may undergo axial deformation, because it is the only deformation that we can have in each member of truss. Truss as a whole the joint may displaced in x and y coordinate, but if you take every member individually, they will undergo only axial deformation, and the work done will be the internal force multiplied by the axial deformation. Now, but in beam, we have neglected the axial deformation. It is the moment, the main deformation mode in beam is bending like this. Okay. So, suppose if you take a same beam AB which is subjected to some external load, and for that load, and it undergoes bending, and then if it is and this is the deflected shape of this beam. Okay. Now, rho is the radius of this deflected shape. Then 1 by rho will be the curvature will be 1, can be written as 1 by rho. Okay. Now, curvature, you have done it probably in your mechanics course. That's if you have done it in your mechanics course, this curvature is equal to how the moment and curvature are related. The curvature is equal to m by EI. You have done this proof in your mechanics course, but still we will be discussing this relation in subsequent weeks when we talk about how to find out deflection for beams, and when we derive the expression for this deflected shape. For the time being, you can take this expression for granted. We will prove this expression in subsequent lectures. Okay. So, this is the curvature which is related to moment as this, and EI is the flexural rigidity. If you remember, in truss case we talk that it is the cross, because in truss it is the internal, the member undergoes axial deformation. It is the cross sectional area of the member which is important, and A into E, A is the cross sectional area, E is the Young's modulus, A into E is called axial rigidity. If for a given member, if A is more, the deformation in the axial deformation of the member will be less. Similarly, EI, since in beam it is the flexure or bending which dominates the deformation behavior, this EI is called flexural rigidity. Okay. Again, we will be having a detailed discussion on flexural rigidity and how the flexural rigidity may affect the deformation behavior of the of beam, that we will discuss in subsequent lectures. Okay. So, this is the curvature, right. Now, then the work done, internal work done will be the moment into curvature. Now, in truss it was a discrete system. You can it was a system which is formed by joining some discrete members, right. But this is a continuous system. So, the summation that we use in the case of truss, instead of summation we will have an integration here. Now, integration of moment, which is the force, internal force, and into the curvature, that gives us the internal work done. Okay. Now, again, depending on which is virtual, whether it is virtual or real, we can have the virtual work. Okay. Now, then okay. Now, let us once we know what is external work, how to determine external work and what is internal work, let us see what is the unit load method in this case. Okay. Now, take the beam AB, which is subjected to some arbitrary loading, and because of this loading it undergoes deformation like this. Okay. Now, take any intermediate point C, this point, and suppose at this point C the displacement is delta C. Okay. Now, if we draw the curvature diagram, suppose this is the curvature diagram. Curvature diagram means, just now we talk about, because of this load, we at any point of any section there will be a moment. Suppose that moment is m, that moment is m, that moment is a, which is function of x, and then the flexural rigidity of the member is EI, which could be also function of x. Okay, function of x, and this is equal to curvature, just now we have seen. Okay. Now, if we plot this curvature, suppose this is the curvature. Now, see, since it is a simply supported beam, moment at A and moment at B is 0. So, moment this point, this will be 0. So, curvature at point A, curvature at point will be 0, and suppose this is the curvature of the beam. Okay. Now, then what we can do is take any point x, and at that point x, suppose this value is mx by EI. That is just now we have seen this. Okay. Now, so this is for this. So, we have a beam which is subjected to some real load, and because of this load the beam undergoes deformation, and corresponding curvature is this. At any given point x, the curvature is given by moment by EI. Okay. Now, take the same beam, and suppose at point C we apply a concentrated load. You remember in truss also, the point where we wanted to determine the displacement, we applied one concentrated load in the direction in which we want to determine the displacement. Okay. So, we apply a force here, and corresponding bending moment diagram will be this, and suppose at any point the bending moment is m into is denoted as small m. Okay. Now, suppose suppose this is the real displacement field. This is the displacement in the beam, deformation in the beam due to the real the actual load. Okay. And this is again the real curvature in the beam, that is due to the actual load. So, this is the real displacement field, and suppose this is a virtual force field. Okay. We applied a virtual force at C, and then corresponding moment diagram will be this. Now, take this as system 1, and if we take this system 2, very similar to truss, only difference is here is, instead of the axial deformation, here we will have moment. There the axial deformation and the internal force gave us the work. Here the product of curvature and moment will give us the work, and that product has to be integrated along the length of the beam, because it is a continuous system. Rest of the thing as a concept, the real displacement field and the virtual force field as a concept, they are very similar to truss. Now, if we take this is system 1 and this is system 2, now apply the principle of virtual work. This is the principle of virtual work. Now, F external, so F external is Fc and F internal will be Mc. So, since this is our force field, external force is F and internal force here is the moment, and corresponding internal force is small mx. So, external force is F, internal force is small mx, and then external displacement is dc. This is the external displacement at dc, which is the real displacement that we want to determine in the real structure when the structure is subject to real load, and the corresponding corresponding internal displacement will be the curvature in the real beam. Okay. So, corresponding internal displacement will be the curvature. Now, if we substitute that, then this gives us f c into d c is equal to integration over a b, length of the beam, and m x into phi x. Now, similar to phi x is equal to m x by e I, we know this is the curvature expression, and if we substitute f c is equal to 1, the same that we did it for truss, then this expression become d c is equal to this, and this is unit load method for beam. Now, if we see a beam has several segments, for instance a frame, then what we can do is we can for instance if we take a frame like this. If we take a frame like this, this is A, B, C, D, that integration has to be performed over A B, over B C, over C D. So, we need to get the expression for moment in A B, expression for moment for B C, and expression for moment for C D, and then that integration has to be performed over each length. Okay, that will be demonstrated when we actually things will be clear when we actually apply this principle to some problem. So, this is unit load method. So, we will not further discuss the unit load method for beams and frames. We take this, the reason why we are not going to apply unit load method in this week, because you see the formulation of this method based on certain expression. For instance, one expression is here, we assume that phi x is equal to phi x with the curvature is equal to m x by e I, m x by e I, right. Now, this we have not yet discussed. So, what we do is first we will discuss all this, and then we will discuss about what is flexural rigidity, and then we will apply the unit load method. That will be done in subsequent weeks. For the time being, this is unit load method. Okay. Now, you have to wait for 2 weeks to apply this unit load method for beam and frame problems. Okay. Now, as I said, the principle of this is the translation of the principle of virtual work into a method which can be used to determine a deflection of truss or deflection of beam at any direction or at any point, right. Now, but the principle of virtual work, the application of principle of virtual work is more wide. It is just not finding the displacement, and more you study the structural mechanics or advanced level of structural engineering, probably better you can appreciate the principle of virtual work. Now, another one important, as I said, principle of virtual work also gives a very interesting insight about the behavior of the structure. Now, before I formally tell you what is that behavior, and let us do one exercise, and through that exercise let us try to understand that behavior. Okay. Now, take one simply supported take a simply supported beam. Okay. This is okay. Now, this length is L, and suppose this is A, this is B, this is B. Now, suppose this is subjected to a concentrated load at any arbitrary point, which is P, a concentrated load, and this distance is A, this distance is A, this distance is A, and this distance is B. So, B is essentially L minus A, okay. This distance is B, and this is the force. Okay. Now, some of the expression that I am going to write here, for the time being you have to take them for granted. Next week when we actually start finding the deflection of beams, then you can appreciate and you can understand those expressions. Now, if I see, this is a statically determinate structure, we can find out what is the bending moment, we can find out what is the support reactions, right. That's what we have done so far. We have not yet discussed how to determine the deflection of this beam, that we will be doing in subsequent lectures. Now, if we do that, there are many methods to determine the deflections. Now, if we find the deflection, then the expression will be like this. expression will be, you see, between 0 to a, between 0 x a, okay, the deflection will be, say y will be, let us y is the deflection, that is equal to p into b into x divided by 6 e I l, then x square plus b square minus l square. You may be thinking suddenly out of nothing where we got this expression, right? We got this expression if we apply any method to find out displacement of beam, that could be conjugate beam theory, direct integration method, or virtual or any other method. You can get this expression. Okay. In order to appreciate the expression, you have to wait 1 more week. Now, similarly, between this, the expression of y will be p into b, pb by 6 ei l, and then x cube minus l square minus b square x minus l by b x minus a whole cube. Okay. This is the expression for displacement. When the displacement, if you substitute x is equal to a here and x is equal to a here, you will see that displacement, both the displacements are same. It says the displacement is continuous. Not only that, if you get the slope of this by differentiating y with respect to x, here also you determine the slope and determine the and find this slope, compute the slope at x is equal to a, you will see that slope is also continuous. So, this is a compatibility, this is the compatibility condition. Okay. Now, the point what we want to make, suppose this is case, this is take now 2 points. Okay. Take 2 points, case 1, 2 cases, case 1, and this is true for any value of a and b, okay, less than equal to less than L. Case 1, we take a is equal to L by 3 and x is equal to L by 2. Okay. And now, what it says? It says that we want to a is equal to L by 3 and we want to find the deflection at x is equal to L by 2. Okay. Now, take case 2 where a is equal to L by 2 and we calculate the deflection at L by 3. Okay. Means what it says, the case 1 is the load is applied at L by 3, we are computing deflection at L by 2, and the case 2 is load is applied at L by 2 and we are calculating deflection at L by 3. Okay. Now, then case 1, for case 1 is for case 1 it is x, it is for case 1, and for case 2 it is a. So, case 2 we need to find out the deflection from this expression. For case 1 this expression will be valid. Okay. Now, so what essentially this means, we take the same beam once again. Now, this is the midpoint of the beam. Okay. And this is say point number this is another point which is at a distance L by 3 and this is at a distance L by 2. Okay. And this is point number 1, this is point number 1, this is point number 2. Okay. Now, what it says, this here the load is applied at point 1 and deflection is calculated at point 2, and in this case just the opposite, load is applied at point 2 and deflection is applied at point 1. Okay. Now, let us find out what is the deflection. Suppose this deflection is d1 d21 and this deflection is d12. d21 means the deflection at point 2 due to load at point 1 and this is deflection at point 1 due to load at point 2. Let us find out what is d21 and d12. So, d21 will be d21, which is case 1, we need to, in order to get d21, from this expression we need to substitute A is equal to L by 3 and naturally B will be L minus A means 2L by 3 and X will be L by 2, and if we do that we get D12 is equal to D21 is equal to 23 P L cube by 1296 EI. Okay, you can determine this a simple substitution in the expression and get the final thing. And similarly, if you get D12, you need to substitute A is equal to L by 2 in this expression, B becomes L by 2 and X is equal to L by 3 in this expression. And if we get it, there will be a minus sign here. Okay, if we get it, this will be minus 23 P L cube by 1296 EI. Okay. Now, you see they are same, means that if I apply load at 1 and calculate deflection at 2, the deflection at 2 due to load at 1 will be same as deflection at 1 due to load at 2 if the force, the applied force is same. Okay. Now, this is one observation, but let us see whether we are getting the similar observation for other cases as well. Now, take the same example which is subjected to a concentrated load again at the mid span, say. So, this distance is L by 2 and this distance is L by 2. Okay. And if you calculate theta, at this point, say theta, this is A, this is A, this is B. If you calculate theta B, then it becomes P by the expression of theta becomes P by 16 EI into 4 x square minus L square, and if you substitute x is equal to 0 here, then you get theta is equal to PL cube PL square by 16 EI. Okay. Now, similarly, if we apply a moment here m and calculate the if this is the deformed shape, calculate this delta at the midspan, delta becomes m L square by 16 EI. Okay. Now, if we take P is equal to m, then what it becomes? It becomes theta is equal to P is equal to m is equal to say Q, then this becomes Q L square by 16 EI and it is also becomes Q L square by 16 EI. Okay. Means again what it said, now here the point 1 is, this is the point 1, this is point 2. So, if we apply a load at point 1, calculate the rotation at point 2 and then apply moment at point 2, calculate deflection at point 1, they are same. This is called, and this is not specific to this case, okay, and this is a very generally you take any structure and this is valid, and this theorem is called Maxwell's reciprocal theorem, and Maxwell's reciprocal theorem, but you know later it was observed that this observation is not only valid for one force, this observation is valid for if you have several forces, then also this observation is valid. And then Betti generalized Maxwell's theorem and proposed a very general reciprocal theorem, and that reciprocal theorem we are going to discuss now. Now, see, I could have told you the theorem and prove it, but before you actually before formally introducing the theorem, if you actually experience that really it is happening, then probably you can appreciate the theorem in a better way, and that's what I wanted to do. Now, let us quickly see what is reciprocal theorem. Now, suppose you have again take a simply supported beam, okay, and take 5 points in it, 1 2 3 4 5. So this is 1 2 3 4 and 5.5, and again consider the same beam and similarly these are 5 points, okay, these are 5 points. Now suppose we apply a load, suppose this system is see, this system is P and this system is Q, okay. How they are different? Suppose we apply in system 1, we apply a force here at point number 1 and we apply force at point number 3, and in system 2 we applied force in point number 2, point number 4 and point number 5. And suppose these forces are, this is force applied at point number 1 in system P, and this is force applied at point number 3 in system 3. Similarly, this is force applied at point number 2 in system 2, and this is force Q4 and this is force Q5. So, in this system the same length, same beam, but only thing is we have applied force at point number 1 and 3, and these forces are denoted as force in system 1 at point number 1, and in system Q we applied the forces other points 2, 4 and 5 is denoted as F in system 2 point number 2, F in system Q point number 4, okay. Now if we take force now, so in both the cases this beam will undergo some deformation, this beam will undergo some deformation and this beam will undergo some deformation, right, undergo some deformation. Now if we take the force in system P and if we assume the force in system P and the displacement in system Q, they are conjugate to each other, then we can apply the principle of virtual force. And what is the principle of virtual force there? Now this becomes that force, what are the forces we have? The force F P1 into, this is the force in system 1, corresponding displacement in system 2, that is the conjugate, means this displacement, suppose this displacement is dq1. So, this become into dq1 plus force in system F P3 into corresponding displacement is this is dq3. So, dq3. So, this is the external work done. If we take this is the system force, external force, and this is the conjugate displacement. So, this will be the external work done, and what will be the internal work done? Internal work done will be then the internal forces in system P, which is MPx, and the displacement in system Q, internal displacement means curvature of system Q. Curvature of system Q means phi of Q x into dx. Okay. Now, this becomes what? We know that phi is equal to phi of Q will be m in system Q of x divided by EI, right. So, this becomes, this is over AB, this becomes MP into MQ divided by EI into dx. Say this is equation number 1. Okay. Now, let us do the opposite. Opposite means that if we take the force in system P, force in system Q is the force and which is conjugate to the displacement in system P, then what will happen? The force Fq2, external work done will be Fq2 into displacement this. This displacement is dP2, force Fq2 into this displacement dP4, force this displacement and this displacement will be dP5. So, displacement in system 5. So, what we have then? We quickly have this, that force in system 2 into corresponding displacement in system P, force in system Q corresponding displacement in system 4, plus force in system 5 corresponding displacement in 5. This will be the external work done. If we take the system Q as force for force field and displacement in system P is the displacement field. So, this force field in system Q is and displacement field in system P are conjugate. Then this will be the internal work done. Internal work done will be, in this case internal work done will be then what? Internal work done will be MQ, the force in system Q, internal force in system Q into displacement in system P. Okay. And this is equal to, what is the displacement? This is MQ x, displaced curvature in system P will be MP of x by EI dx is equal to MPx MQx by EI dx integration. You see, we also obtain this similar expression in this is 2. Okay. Then what it says? This says that if we take, this says that if we, these two are same, right? These two are same, this and these are same. What is this? This is force in system Q. If we force in system Q and displacement in system P, and their work done should equal to force in system P and displacement in system Q. Okay. So, if you take force field in system Q and conjugate displacement in system P, whatever conjugate displacement in system P, whatever work done we have, and if we take the opposite, means the force field in system P and displacement in system Q, they are conjugate, the work done what we get, that work done will be same. That is the reciprocal, Betti's reciprocal theorem, which is a general version of the reciprocal theorem. Just now we have experienced through one example, right. So, the reciprocal theorem is this: in a linear elastic structure, the total external virtual work associated with force Fp, two system if you take, this is system P, this is system Q, the forces acting system P is, the two forces are acting in system P and one force is acting at system Q. We have 3 points, point 1, point 2 and point 3. In system 1, in system P we have force at point 1 and point 3, and in system 2 we have force at point 2. Now, displacement at point 2 in system P is dP2 and corresponding displacement at point 1 and point 3 in system 3 is Q1 and Q3. And what this theorem says, that this multiplied by this multiplied by this multiplied by this plus this multiplied by this means work done by this force and conjugate displacement, this force and corresponding conjugate displacement will be equal to the work done by this force and corresponding conjugate displacement. And this is the Betti's reciprocal theorem, which is the general version of the reciprocal theorem of that proposed by Maxwell. If you look at the year it was proposed in 1872. Now, let us see what is the Maxwell version. Maxwell version is the very special case of Betti's reciprocal theorem. What you see, this is proposing much earlier than the Betti's generalization. It was proposed in 1864 for just one force and one displacement case, and then later it was generalized by Betti in 72, and that generalized version we have just now discussed. Now, what is this is the general version of the this is Betti's reciprocal theorem. Now, from that, if we just remove the third point, okay. Now we have two forces and two displacement, corresponding displacement. Now, make this force and this force same. Okay. Now, this point is point number 1, this point is point number 1, this point is point number 2. Similarly, this point is point number 1 and this point is point number 2. Then, since dq3 is gone, so this becomes 0. So, we have two forces and two displacement. Now, in first case, force is acting at point number 1 and displacement and then okay, and then if we and displacement, these are the one displacement and displacement at 2. Now, what we have is, if this becomes 0 and then the expression, now this also becomes f, this becomes f, this becomes F, and this also becomes F, because now the forces are same. This F and this F gets cancelled out, and then we have dq1 is equal to dp2, means this displacement is equal to this displacement. Now, what is this displacement? This displacement is the force acting at 1 and measure the displacement at 2. Here force acting at 2 and measure the displacement at 1. This is the Maxwell's reciprocal theorem, and we observed through a beam problem just now, right? This is the beam problem. This is the beam problem. We demonstrated that theorem, right? This is the same theorem obtained from a general version of the reciprocal theorem. So, Maxwell's reciprocal theorem is a general version of this of the Betti's reciprocal theorem. Now, as I said, I started this course by this lecture by saying that this reciprocal theorem, virtual work principle, gives insight, very interesting insight into the structural behavior, and that insight is the reciprocal theorem. But what is the physical interpretation of the reciprocal theorem? To start with, I leave it to you to think about it. We'll again come to this reciprocal theorem and discuss what is the physical interpretation of this theory and how this structural behavior, this property of the structure makes our life easier. We'll discuss this when we learn displacement based or force based method for solving, or in general the matrix method of structural analysis, direct stiffness method of structural analysis towards the end of this course. For the time being, I leave it to you. Please think what physical interpretation it may in what way this information is we can use this information in our structural analysis. Okay, I stop here today. What we'll do, as I said, this is the last class of this week. Next week what we do is we'll start how to find out deflections of beam and frame. We'll learn various methods, and one method will be the virtual work principle, unit load method. There we will have some demonstration of the unit load method for beams and frames. Okay, see you in the next week. Thank you.